Somewhere out in the dark between the stars, there is an object that almost became a sun, and failed. It glows a deep, sullen crimson, far too dim to be called a true star, yet far too massive and furious to be called a planet. And if you could somehow descend into its skies, you would witness weather stranger than anything that has ever fallen on Earth. Here, the clouds are not made of water. They are made of vaporized rock and molten metal. Droplets of liquid iron condense high in the air and fall as scalding rain. Sheets of silicate glass drift sideways on winds hotter than a blast furnace. And the deeper you sink, the more impossible it becomes. This is a brown dwarf, one of the most bizarre objects in the entire cosmos. And tonight, we are going inside one. Before we descend into these strange skies, if you find this kind of journey into the unknown fascinating, a quick like or subscribe really does help this little channel keep growing. It's a small gesture on your end, but it genuinely makes a big difference for me. Now, let's begin. Let me start with a simple question, because the answer is far stranger than it sounds. What is the difference between a planet and a star? Most of us carry an easy answer in our heads. A star is a sun. It burns. It shines with its own light. It is a furnace pouring heat and brightness into the dark. A planet, by contrast, is cold. It produces almost no light of its own. It simply orbits its star and reflects whatever glow happens to fall on it. The line between the two seems obvious, almost childishly clear. Stars make light. Planets do not. One is a fire, the other is a rock or a ball of gas circling that fire from a respectful distance. But the universe does not actually draw the line so neatly. Out there in the cold spaces between the stars, there exist objects that refuse to obey this simple rule. They are too large, too massive, and far too hot to be ordinary planets. Yet they are too small, too feeble, and far too dim to be considered true stars. They sit in the forbidden middle ground, in a kind of cosmic no man's land that nature was not supposed to allow. We call these objects brown dwarfs, and they are some of the most mysterious bodies in the entire cosmos. The name itself is a little misleading, and it is worth clearing up right away. A brown dwarf is not actually brown. If you could float in space beside one and look at it with your own eyes, you would not see a chocolate-colored sphere. You would see something closer to a deep, sullen red, or in the cooler cases, a faint dull crimson fading into near darkness, like the last ember of a dying campfire glimpsed across a black field at midnight. The word brown was chosen decades ago almost as a placeholder, a way of saying this object is dimmer and cooler and more muted than a red star, something between red and black, something hard to name. The name stuck, even though it was never quite accurate. The coolest of these objects may even glow a faint magenta rather than red. But forget the colour for now. What matters is the nature of the thing. To understand a brown dwarf, you first have to understand how stars are born, because a brown dwarf begins its life in exactly the same way a star does. It does not form like a planet. This is one of the most important things to grasp, and it is where the strangeness truly begins. Planets, as far as we understand them, are built from the bottom up. They assemble themselves piece by piece inside the swirling disk of leftover gas and dust that surrounds a young star. Tiny grains stick together to form pebbles. Pebbles collide and clump into boulders. Boulders gather into mountains, and mountains into worlds. It is a slow, patient process of accumulation, of small things gathering into large things over millions of years, until a planet emerges. A brown dwarf does not do this. A brown dwarf forms from the top down, the way a star does, by the collapse of an enormous cloud. Scattered across our galaxy are vast clouds of cold gas and dust, regions so large and so cold, and so faint that light struggles to escape them. These are the nurseries of stars. Each cloud is mostly hydrogen, the simplest and most common element in the universe, with a scattering of helium and a faint dusting of heavier elements left behind by stars that lived and died long ago. For long stretches of time, these clouds simply drift, held in a delicate balance. The inward pull of their own gravity is matched by the outward push of their internal pressure and motion. Nothing happens. They wait. But balance does not last forever. Something disturbs the cloud. Perhaps a nearby star explodes in a supernova, sending a shock wave rolling through the gas. Perhaps two clouds drift into one another and collide. Perhaps the slow turning of the galaxy itself squeezes the cloud as it passes through a spiral arm. Whatever the trigger, a region of the cloud becomes a little too dense, and gravity begins to win. That dense knot starts to collapse inward, pulling more and more material toward its center. And as it falls inward, it heats up. This is one of the great secrets of the cosmos. A rule that will matter enormously for everything we are about to explore. When gravity pulls matter together, that matter does not fall in quietly. It releases energy. Falling material gains speed. Speed becomes heat. The deeper and tighter the collapse, the hotter the center becomes. So the collapsing core of the cloud begins to warm. At first it is merely less cold, then it grows genuinely warm, then hot, then searing. The center of this collapsing knot becomes a glowing ball of compressed gas, growing denser and hotter with every passing moment, squeezing itself tighter under the relentless inward pull of its own gravity. This glowing object is called a protostar, a star in the making, an embryo of a sun. And up to this point, the story of a brown dwarf and the story of a true star are completely identical. They begin the same way. They are siblings born of the same process. The difference between them comes down to a single quantity, and that quantity is mass. Here is the moment that decides everything. As the protostar's core continues to heat under the crushing weight of all the material piled on top of it, it approaches a threshold. If the core can become hot enough and dense enough, something miraculous happens at its very center. The hydrogen there begins to fuse. The atomic nuclei, normally repelled from one another by their shared positive charge, are slammed together so hard and so fast that they overcome that repulsion and merge, forming helium and releasing a flood of energy in the process. This is nuclear fusion, the same reaction that powers our sun and every star you have ever seen in the night sky. And once it begins, once that fire is lit, it changes the object forever. The energy pouring out of the fusing core pushes outward against gravity's inward crush, and the two forces settle into a long, stable standoff. The object stops collapsing. It steadies itself. It begins to shine, not from the fading heat of its birth, but from a fire it can now feed and sustain for millions, billions, even trillions of years. A star has been born. But why should this ignition be so difficult to achieve? Why does it demand such crushing heat and such enormous mass before the fire will catch? The answer lies in a stubborn fact about the hearts of atoms. To fuse two hydrogen nuclei together, you must bring them into direct contact, close enough that they merge into a single heavier nucleus. The trouble is that every hydrogen nucleus carries a positive electric charge, and positive charges repel one another fiercely, The closer you push two of them together, the harder they shove back apart, like two magnets turned the wrong way round, resisting your every effort to unite them. This electrical resistance forms a kind of wall, an invisible barrier standing between the nuclei and the fusion you are trying to force. To smash through that wall, the nuclei must collide at staggering speeds, and the only way to make them move that fast is to heat the gas to extraordinary temperatures, because heat is nothing more than the motion of particles. The hotter the core, the faster the nuclei fly, and the harder they crash into one another. Only when the temperature climbs into the millions of degrees do the collisions become violent enough to breach the barrier and allow fusion to begin. There is even a subtle quantum trick that helps the process along, a phenomenon called tunneling, in which a nucleus can occasionally slip through the electrical barrier rather than smashing over the top of it, almost as if it borrowed a secret passage through a wall it could not otherwise climb. Without this quantum assistance, stars would need to be hotter still to shine at all. But even with it, the threshold remains brutally high. A core simply cannot reach the necessary temperature unless an enormous weight of overlying gas is pressing down upon it, compressing it and heating it toward that critical point. And that is why mass is everything. Gather enough mass, and the weight ignites the core. Fall short and the barrier holds. The nuclei never quite collide hard enough, and the fire is never lit. The brown dwarf is the object that fell short, the core that never grew hot enough to breach the wall. But this miracle has a price of admission, and the price is mass. To squeeze a core hot enough and dense enough to ignite sustained hydrogen fusion, you need a great deal of material pressing down from above. You need weight. You need the gravity of an enormous amount of gas bearing down on that central point. And if the collapsing object simply does not gather enough mass, the core never reaches the critical temperature. The fire never catches. The threshold for this, the dividing line between success and failure, sits at roughly 80 times the mass of Jupiter, the largest planet in our own solar system. That is the magic number. Gather more than about 80 Jupiter masses of gas, and your core ignites, and you become a true star, a self-sustaining sun. Gather less than that, and no matter how hot your birth was, no matter how furiously you glowed in your youth, your central fire sputters and fails. You become a brown dwarf, the star that never quite switched on. Think about how close that is. Think about how narrow the margin truly is. An object with 79 times the mass of Jupiter is a brown dwarf, a failed star, doomed to fade. An object with 81 times the mass of Jupiter is a true red star, destined to shine for trillions of years. The difference between them is barely a rounding error in cosmic terms. It is the difference between a match that catches and a match that does not, decided by the faintest whisper of extra mass. The brown dwarf reached for stardom and missed by the smallest possible margin. It is, in the most literal sense, a star that almost was. Now, you might reasonably ask a question at this point. If the brown dwarf failed to ignite its core, if the great fire never caught, then why does it glow at all? Why is it not simply a cold, dark, dead ball of gas drifting silently in the void? If there's no fusion engine running inside it, where does its warmth and its dim red light come from? This is one of the most beautiful parts of the whole story, and the answer reaches all the way back to that moment of collapse. Remember the rule? When gravity pulls matter together, that matter releases energy as heat. The brown dwarf was born from an enormous collapse, an infalling of gas that grew hotter and hotter as it compressed. All of that heat, all of that energy gathered during its violent birth, did not simply vanish when the collapse slowed. It was stored inside the object, locked into the searing hot gas of its interior. A brown dwarf, in other words, is born red hot. It enters the universe glowing fiercely, not from any fire it can sustain, but from the sheer leftover heat of its own creation. And in the long ages that follow, it does something very simple and very poignant. It cools. A brown dwarf spends its entire existence slowly radiating away the warmth of its birth, leaking heat into the cold of space, growing dimmer and cooler century by century, eon by eon. It is like a coal pulled from a fire and left on the hearth. For a long time after the flames are gone, that coal still glows, still radiates warmth, still gives off a faint orange light in the darkness. It is not burning anymore. It has no fuel. It is simply releasing the heat it already holds, slowly surrendering it to the surrounding air. A brown dwarf is that coal, scaled up to a body larger than the planet Jupiter, glowing for a span of time that dwarfs the entire history of life on Earth. But the leftover heat of birth is not the only source of a brown dwarf's warmth, and the second source is just as elegant. Even after it stops collapsing dramatically, a brown dwarf continues to shrink, very gently, very slowly, over enormous stretches of time. Its own gravity never stops pulling. And so the object keeps compressing itself, squeezing itself into a slightly tighter ball across millions of years. And every time gravity wins a little more, every time the object contracts even slightly, that same old rule applies once again. Compression releases heat. This slow, patient self-squeezing generates a steady trickle of warmth from within, a process named after two physicists who first worked out its details, sometimes called Kelvin-Helmholtz contraction. It is gravity itself, acting as a kind of slow furnace, gently warming the object from the inside as it slowly collapses under its own weight. So a brown dwarf is heated twice over by its own gravity, once in the great heat of its birth, and then continuously, faintly, by the never-ending squeeze of its own contraction. There is even a third source of warmth, and it is the closest a brown dwarf ever comes to acting like a true star. While a brown dwarf cannot fuse ordinary hydrogen, the most massive ones can, for a brief window early in their lives, fuse a special and rarer form of hydrogen called deuterium. Deuterium is sometimes called heavy hydrogen because its nucleus carries not just the single proton of normal hydrogen, but a neutron alongside it. This extra neutron makes deuterium far easier to fuse than ordinary hydrogen. It catches fire, so to speak, at a much lower temperature, a temperature that even a failed star can reach in its hot, youthful core. And so, for a few million years near the beginning of its life, a young brown dwarf can fuse the small amount of deuterium it contains, releasing a modest extra glow of energy. But there is a cruel catch. Deuterium is extraordinarily rare. The universe contains only a tiny trace of it, a few parts in 100,000 of all hydrogen. A brown dwarf burns through its meager deuterium supply quickly in a cosmic eye blink, and then that flame too goes out, leaving the object once again to rely on the slow fading warmth of its birth and its gravity. Think of the contrast. A few million years of deuterium fusion, a brief flicker of borrowed starlight near the very beginning, set against a future of cooling that stretches across trillions of years. For one short chapter, the object almost behaves like a star. and then it spends the rest of eternity slowly surrendering that warmth to the dark. This deuterium fusion is actually so important that astronomers use it to draw the lower boundary of what counts as a brown dwarf at all, just as roughly 80 Jupiter masses marks the upper line. The place where true stardom begins, there is a lower line as well, sitting at around 13 times the mass of Jupiter. Below that mass, an object cannot even fuse deuterium. It can do nothing but cool. And many astronomers say that below this line, you are no longer dealing with a brown dwarf at all, but with a very large planet. So the entire category of brown dwarfs lives in this narrow band, this strange middle kingdom, stretching from about 13 Jupiter masses at the bottom to about 80 Jupiter masses at the top. Above it lie the stars, below it lie the planets, and in between sits this peculiar population of objects that belong fully to neither world. Now I want you to pause and appreciate just how odd these things are when you try to picture one. You might assume that an object more massive than Jupiter would also be much, much larger than Jupiter. More mass should mean more size. That is how things work in our everyday experience. A heavier object is usually a bigger object, but brown dwarfs break this intuition in a way that is genuinely astonishing. A brown dwarf with 13 times the mass of Jupiter and a brown dwarf with 70 times the mass of Jupiter are very nearly the same size. In fact, almost every brown dwarf in existence, no matter how much mass it holds, is roughly the same diameter as Jupiter itself. You could take an object packing dozens of times Jupiter's material, and it would be barely wider than Jupiter is today. How can this possibly be? How can you pour 70 times more material into a ball without making the ball bigger? The answer lies deep in the physics of crushed matter, and it gives us our first real hint of just how extreme the inside of a brown dwarf truly is. As you add more and more mass, you also add more and more gravity, and that extra gravity crushes the object's interior with ever greater force. At a certain point, the matter inside becomes so compressed that it can barely be squeezed any further. It resists, pushing back through a strange quantum effect that we will explore in detail when we descend into the interior. The result is a kind of cosmic balancing act. Add more mass and you add more crushing gravity, but you also add more of this resisting pressure, and the two roughly cancel out. The object does not grow, it simply becomes denser, packing more and more matter into nearly the same volume. So the heaviest brown dwarfs are not the largest. They are the densest, the most tightly crushed, with material inside squeezed to a degree that has no parallel anywhere on Earth. This is part of what makes a brown dwarf so hard to find and so hard to study. It is small, barely the size of a single large planet. It is dim, often glowing only feebly in the deep red and the infrared, the kind of light our eyes cannot even see. And it is cold, at least by the standards of stars. The hottest, youngest, most massive brown dwarfs might have surface temperatures of a couple thousand degrees, glowing a tired red. But the coolest ones, the old and faded ones, can be shockingly cold. Some of the chilliest brown dwarfs ever discovered have surface temperatures no hotter than a cup of tea, or a warm summer afternoon, or even room temperature. Imagine that. An object more massive than Jupiter, born from the collapse of a star-forming cloud, a sibling of the stars themselves, yet so cool on its outer surface that its glow registers no hotter than a warm oven, or, in the very coldest cases, barely warmer than a summer afternoon. These colder specimens are so faint and so dark that they were nearly invisible to us until very recently. hidden ghosts drifting in the spaces between the brighter stars. For a long time, in fact, brown dwarfs were purely theoretical. Scientists predicted that such objects ought to exist. The logic was sound. If clouds collapse to form stars, and if the smallest collapses simply fail to ignite, then there should be a whole population of failed stars scattered across the galaxy, glowing faintly, waiting to be found. The idea was proposed back in the 1960s, but predicting something and actually finding it are two very different challenges. These objects were so dim and so cool that for decades our telescopes simply could not see them. They were too faint, lost in the glare of brighter stars, radiating most of their light in infrared wavelengths that were difficult to detect. The hunt stretched on for years, and many began to wonder whether these failed stars truly existed at all, or whether they were merely a tidy idea that nature had declined to actually build. The reason the search proved so maddeningly difficult comes down to the nature of the light these objects emit. A brown dwarf is so cool that it radiates most of its energy not as visible light, the kind our eyes can see, but as infrared light. A form of radiation that lies just beyond the red end of the rainbow, invisible to the human eye and difficult for early telescopes to capture. To find these failed stars, astronomers needed instruments that could see in the infrared, detectors sensitive to this hidden warmth, and for a long time such technology was either crude or simply did not exist. There was a further problem. Many brown dwarfs orbit close to ordinary stars, and the glare of a bright star can easily drown out the feeble glow of a dim companion beside it, the way the headlights of an oncoming car can hide a candle flame held next to them. Picking out the faint ember of a brown dwarf from the blazing light of a nearby star demanded both patience and precision that the astronomers of earlier decades simply could not muster. It was only as infrared detectors matured, and as great sky surveys began systematically scanning the heavens for sources of this hidden warmth, that the failed stars finally began to reveal themselves. And once the floodgates opened, the discoveries came thick and fast. What had been a single confirmed object became a handful, then dozens, then hundreds, then thousands, as survey after survey swept the sky and turned up these dim red embers in ever greater numbers. The realization slowly dawned that these objects were not rare freaks at all, but an enormous and previously hidden population, with current surveys suggesting the Milky Way may hold tens of billions of them, an entire substellar census that had gone uncounted for the whole of human history, waiting only for eyes that could see its hidden glow. Then, finally, in the mid-1990s, the breakthrough came. In 1995, astronomers confirmed the discovery of an object that fit the profile perfectly. A faint companion orbiting a small star, an object far too dim and too cool to be a star itself, yet clearly a substantial body. One of the most famous of these early finds was a brown dwarf circling a nearby red star, a faint speck designated by a catalogue number that we can simply think of as one of the first confirmed failed stars ever seen. Its discovery was a landmark moment. It proved, at last, that these in-between worlds were real, that the theoretical predictions had been correct, and that the galaxy was indeed populated by countless objects caught forever in the gap between planet and star. Since then, our instruments have grown vastly more powerful, especially our infrared eyes, and we have found these objects in enormous numbers. It now seems likely that brown dwarfs are extraordinarily common, perhaps nearly as numerous as the stars themselves. A vast hidden population of failed suns drifting quietly through the dark. And here's a thought that should give you a small shiver. Because they're so faint and so cold. Because they emit so little light. Some of these brown dwarfs may be drifting much closer to us than we realize. One of the nearest known systems to our own sun is not a single bright star, but a pair of brown dwarfs. Two failed suns orbiting one another just a handful of light years away. So dim that we did not even notice them until relatively recently, hiding almost in plain sight in our cosmic neighborhood. The dark between the stars, it turns out, is not as empty as it looks. It is sprinkled with these dim red embers, these almost stars glowing too softly for us to easily see. So this is the object we are about to enter. Let us hold its portrait in our minds clearly before we begin our descent, because everything that follows depends on understanding what this thing fundamentally is. It is a sphere of gas, mostly hydrogen and helium, roughly the size of the planet Jupiter, yet holding anywhere from 13 to 80 times Jupiter's mass crushed inside that modest volume. It was born exactly as a star is born, from the collapse of a great cold cloud, and for a few brilliant moments of its youth, it may have flickered with the fusion of deuterium. But it never gathered enough mass to ignite the steady hydrogen fire that defines a true star, and so its central furnace failed to light. It glows now not with the fire of fusion, but with the slowly fading heat of its own creation, warmed gently from within by the endless squeeze of its own gravity, cooling across spans of time so long they make the age of our species seem like a single heartbeat. It is dim. It is dense beyond imagining at its core, and depending on its age, its surface might be a glowing red inferno or a strangely cool and shadowed expanse. But none of these facts, remarkable as they are the reason we have come. We have not journeyed out here merely to admire a failed star from a safe distance. We have come because of what is happening in its skies. Because this object, this crushed and cooling sphere caught between two worlds, possesses an atmosphere unlike anything that exists on any planet we know. The strange in-between nature of the brown dwarf, its peculiar combination of intense interior heat and a relatively cool outer surface, creates exactly the right conditions for a kind of weather that should not be possible. A weather of vaporized rock and molten metal, of clouds made of minerals and rain made of iron. To understand that weather, to truly grasp how it forms and why, we cannot simply hover at the surface. We have to go deeper. We have to leave the cold of space behind and begin our descent into the furnace, down through the layers of this impossible object, toward the crushing, glowing heart that drives everything we are about to witness. The portrait is complete. The strangest part of the journey is just beginning. We are standing now at the very top of the atmosphere, hovering just above the visible surface of our failed star. And before we fall, I want you to understand something that will turn your intuition completely upside down. When you imagine the inside of any object that glows, your mind almost certainly pictures fire. You picture flames. You picture a churning, blazing inferno, a roaring furnace of open burning, the way the inside of a star is so often drawn. But the inside of a brown dwarf is nothing like that. There are no flames down there. There is no open fire. What waits beneath us is far stranger, far quieter, and in many ways far more violent than any fire could ever be. We are about to descend not into a furnace of flames, but into an ocean of crushed matter. a place where the very rules of ordinary substance break down. So take a breath, steady yourself, and let us begin to fall. The first thing you would notice as you sink below the visible surface is that there is no surface. Not really. Not in the way you might expect. On Earth, when you descend from the sky, you eventually strike the ground, a hard and definite boundary between the air above and the solid rock below. There is a clear line. One moment you are in the atmosphere, the next you are standing on solid Earth. A brown dwarf has no such line. It is a ball of gas, and as you descend, that gas simply grows thicker, denser, and hotter around you, with no sharp transition anywhere to mark where the atmosphere ends and the body of the object begins. What we call the surface is really just the depth at which the gas becomes opaque enough to glow. The layer from which the object's faint red light escapes into space. It is a surface of appearance, not a surface of substance. Sink below it, and you simply keep falling through ever-thickening gas, with the pressure mounting and the heat raising with every kilometer you drop. And rise it does, with astonishing speed. At the visible surface, depending on the age of our brown dwarf, the temperature might be anywhere from a glowing red heat of around 2000 degrees down to something far cooler. But as you fall, the temperature climbs relentlessly. Within a relatively short distance below the surface, the heat builds into the thousands of degrees, then climbs into the tens of thousands. The deeper you go, the hotter it becomes, a steady and unforgiving increase that never lets up as you sink toward the center. This is not the heat of fire. It is the heat of compression, the heat of all that overlying material pressing down, the stored warmth of the object's birth concentrated and intensified toward the core. By the time you reach the deep interior, the temperature can soar into the hundreds of thousands, and at the very heart of a substantial brown dwarf, the central temperature can reach into the millions of degrees. Millions. Hot enough that you might think fusion should surely catch. And in the most massive brown dwarfs, the core does flirt with that threshold, fusing deuterium for a time, almost but never quite reaching the steady hydrogen fire of a true star. But heat is only half of the story of this descent, and in many ways it is the lesser half. The truly mind-bending change as you fall is not the temperature, it is the pressure. Pressure is simply the weight of everything above you pressing down. On Earth, the entire atmosphere, the whole column of air stretching from the ground up to the edge of space, presses down on your body with what we call one atmosphere of pressure. You do not feel it because you evolved within it, but it is there, the weight of all that air bearing down on every square inch of you. If you dive into the ocean, the pressure climbs quickly. Just 10 meters down, the weight of the water doubles the pressure on your body. Dive deep enough to the crushing blackness of the ocean trenches, and the pressure becomes so immense it can implode a steel submarine, squeezing it like a fist closing on an egg. That is the pressure at the bottom of Earth's deepest sea, 1,000 times the pressure at the surface. It helps to imagine this descent not as a single smooth fall, but as a passage through distinct realms, each stranger than the last. In the highest reaches where we began, the material behaves much like an ordinary gas, thin and translucent, the kind of atmosphere we might almost recognize, but sink a little deeper, and the gas grows so dense and so warm that it crosses into a peculiar state physicists call supercritical, a condition in which there is no longer any real distinction between a gas and a liquid. The material is too hot and too compressed to be either one cleanly. It is a thick, soupy fluid that fills all the space available to it like a gas, yet flows and presses like a liquid. There is no shoreline here, no sloshing sea with a clear top. There is only this seamless thickening, a gas that becomes a fluid without ever passing through a moment you could point to and call the surface of an ocean. Deeper still, and even this supercritical fluid gives way as the pressure mounts past the point where ordinary matter can survive, into the crushed and degenerate realm that forms the true body of the world. 3 realms then, blending one into the next without a single hard boundary anywhere along the way, each marking a stage in the slow surrender of matter to the monstrous weight pressing down from above. Now, hold that image of crushing oceanic pressure in your mind and then throw it away, because it is nothing. It is a gentle caress compared to what waits inside a brown dwarf. As you descend through these thickening layers of gas, the pressure does not merely double or triple. It multiplies again and again, building with terrifying speed. By the time you have sunk well into the interior, the pressure around you has climbed to thousands of times Earth's surface pressure, then millions of times, then far beyond. At the core of a brown dwarf, the pressure reaches levels measured not in millions, but in hundreds of millions, even billions of times the atmospheric pressure you feel right now on Earth. Some estimates place the central pressure of a massive brown dwarf at numbers so large they lose all ordinary meaning, pressures crushing the matter at the center, with a force that has no equivalent anywhere in our daily experience. There is nothing on Earth, nothing in our entire solar system outside of the giant planets and the sun, that can compare to the squeeze at the heart of this failed star. And it is this colossal pressure, far more than the heat, that does something extraordinary to the matter inside. To understand it, we have to talk about what happens to a gas when you crush it hard enough, because the answer defies common sense. Picture the hydrogen gas that makes up most of the brown dwarf. In its ordinary state, a gas is mostly empty space. The atoms or molecules within it fly about freely, widely separated, colliding now and then, but mostly drifting through emptiness. That is why gas is so easy to compress. You are mostly just squeezing out the empty space between the particles. Push them closer together and the gas becomes denser. Keep pushing and it becomes denser still. On Earth, with the modest pressures we can generate, you can compress a gas a great deal, packing those particles tighter and tighter. But inside a brown dwarf, the pressure is so unimaginably vast that the particles get squeezed practically against one another, packed so densely that almost no empty space remains between them. And here is where the ordinary rules collapse and something genuinely bizarre takes over. When matter is crushed this severely, a strange quantum phenomenon emerges, one of the deepest and most counterintuitive truths in all of physics. It turns out that the tiny particles called electrons, which surround every atomic nucleus, absolutely refuse to be packed too closely together. This is not because they repel one another through their electric charge, though they do that too. It is something far stranger and far more absolute. It is a fundamental law of nature, sometimes called the exclusion principle, which states that no 2 electrons can ever occupy exactly the same state in the same place at the same time. Each electron demands its own private space, its own unique quantum identity, and it will not, under any circumstances, share it. When you crush matter hard enough, You try to force these electrons into the same tiny spaces, and they will not allow it. They push back. And the resistance they generate is staggering. A pressure of pure quantum defiance that has nothing to do with heat or motion. A pressure that exists simply because the electrons refuse to be crowded. This is called electron-degeneracy pressure, and it is one of the most important forces in the entire universe. It is the force that holds up burned-out stars. It is the force that resists the crush of gravity in the dead cores of suns. And it is the force that determines the entire structure of a brown dwarf. The matter inside a brown dwarf is squeezed so hard that it becomes what physicists call electron-degenerate matter. A state of substance in which the electrons are packed to their absolute quantum limit, pushing back against gravity not because they are hot, but because the laws of quantum mechanics simply forbid them from being squeezed any further. This single fact explains the great mystery we touched on earlier, the puzzle of why brown dwarfs are all roughly the same size, no matter how much mass they hold. Now you can see the answer with perfect clarity. In a normal object, adding more mass means adding more weight, which means the object should compress and shrink. But in degenerate matter, the electron degeneracy pressure pushes back harder the more you compress it. So when you add mass to a brown dwarf, you do add more crushing gravity, but you also trigger more fierce quantum resistance from the electrons, and the two effects very nearly cancel out. The object becomes denser, packing more matter into the same space, but it barely changes size at all. This is why you can pour 70 times Jupiter's mass into a ball that remains nearly Jupiter's width. The matter inside is not behaving like ordinary gas anymore. It is behaving like this strange, defiant, quantum-crushed substance, governed by rules that have no place in our everyday world. If the strangeness of this defiant matter is hard to hold in the mind, here is a way to picture it. Imagine an enormous auditorium in which there is a strict rule. Every seat may hold only one person, and no two people may ever share a seat or stand in the aisle. As more and more people pour into the auditorium, they fill the seats one by one, the lowest and most comfortable first, then the higher ones, then the ones near the very back. When every seat is taken, the crowd cannot be packed any tighter, no matter how forcefully you push at the doors, because there is simply nowhere left for anyone to go. The crowd pushes back against the doors not because the people are warm or restless, but because the rule itself forbids any further crowding. The electrons inside a brown dwarf are like that crowd. Crushed to their absolute limit by the weight of the world above them, they fill every available state right up to the brim, and then they refuse, absolutely and by the deepest law of nature, to be packed any closer. That refusal is the pressure that holds the brown dwarf up. A pressure born not of heat or fire, but of one of the deepest and most unbending laws in all of physics, written into the very fabric of how matter is built. And it gets stranger still, because at these pressures, the hydrogen itself transforms into something we never encounter on Earth. We normally think of hydrogen as a gas, light and invisible, the stuff that fills balloons and burns in the sun. But when you crush hydrogen with the monstrous pressure found inside a brown dwarf, it changes its very nature. The pressure becomes so intense that the hydrogen atoms can no longer hold onto their electrons in the ordinary way. The electrons are squeezed loose and begin to flow freely through the crushed material, exactly the way electrons flow freely through a piece of metal. This transformed hydrogen, which conducts electricity and behaves in many ways like a liquid metal, is called metallic hydrogen. It is one of the most exotic substances in the cosmos, a form of hydrogen that exists nowhere on the surface of our planet, that we can barely create for fleeting instants in our most extreme laboratory experiments, and yet which makes up the vast bulk of a brown dwarf's interior. So as you sink toward the core, the gas around you gradually gives way to this dense, dark, metallic ocean of crushed hydrogen, a liquid-like substance shimmering with free-flowing electrons, packed to densities that would crush any earthly material into oblivion. This metallic hydrogen does something else, something we have not yet touched upon, and it gives the brown dwarf a hidden power that reaches far beyond its surface. Because this crushed hydrogen conducts electricity, because its freed electrons flow through it like the current in a wire, the great churning currents of the convective engine are not merely moving heat, they are moving an electrically conducting fluid. And whenever you set a conducting fluid into motion, especially in a rapidly spinning body, you create the conditions for a dynamo, a natural generator of magnetism. The same basic process that gives the Earth its magnetic field, the swirling of molten metal deep in our planet's core, operates inside the brown dwarf on a far grander scale, in an ocean of metallic hydrogen vastly larger than the Earth's entire core. The result is a magnetic field of tremendous strength, in many cases thousands of times stronger than the Earth's own field, wrapping the whole object in invisible lines of force that arc out into the surrounding space. And this magnetism is not silent. On some brown dwarfs, charged particles caught in these powerful magnetic fields are channeled down toward the magnetic poles, where they slam into the upper atmosphere and unleash bursts of energy, including pulses of radio waves that we can detect from light years away. Astronomers have actually picked up these radio signals from certain brown dwarfs, regular pulses beating out the rhythm of the object's rotation as its magnetic poles sweep past our line of sight. A kind of cosmic lighthouse built from a failed star's hidden magnetism. On the very coolest of these objects, the same process is thought to produce aurorae, glowing curtains of light at the magnetic poles, the same phenomenon that paints the skies of the Earth with the northern and southern lights, here playing out on a body that drifts alone in the dark with no star nearby to feed it. So the metallic ocean at the heart of the brown dwarf does more than hold the world up against gravity. It makes the object a magnet and a beacon, glowing and pulsing with a power born entirely from the motion of its own crushed interior. I want you to truly sit with this image, because it is so different from what we expected when we began our descent. We did not find a furnace of flames. We found an ocean, a vast, deep, lightless ocean of metallic hydrogen, crushed to extraordinary density, glowing not with fire but with sheer heat, held up against the relentless pull of gravity not by any burning, but by the stubborn quantum refusal of its electrons to be squeezed together. This is the true body of a brown dwarf. Beneath the thin outer skin of atmosphere where the weather happens, the great majority of the object is this strange degenerate sea, hot beyond description, dense beyond imagining, and utterly silent of any flame. The brown dwarf does not burn. It smoulders. It is a cold, dark ember the size of a giant planet. Its interior a crushed metallic ocean that will slowly cool over spans of time longer than the current age of the universe itself. But a silent ocean of crushed matter by itself would never give us the spectacular weather we came here to see. A still, motionless interior would simply sit there, leaking its heat slowly into space. For there to be weather, for there to be clouds of metal and rain of iron in the skies far above, something has to move. Energy has to flow. Heat has to travel from the scorching depths up toward the cooler surface, and the manner in which it travels turns out to be the hidden engine that drives everything. So let us now turn from the structure of the interior to its motion, to the great currents that stir this crushed ocean and carry its heat upward toward the sky. There are a few different ways that heat can travel through any material, and to understand the brown dwarf, we need to focus on the most dramatic of them. The first way heat can move is through direct contact. The way the handle of a metal spoon grows warm when you leave it in a hot pot. Heat simply passes from particle to particle, conducting through the material. The second way is through radiation. The way you feel the warmth of the sun on your face, even across the vast emptiness of space, energy traveling as light. But there is a third way, and it is the one that matters most here. It is the way that a pot of water churns and roils as it heats on a stove. It is called convection, and it is the great mover of heat inside a brown dwarf. Picture that pot of water on the stove again, because it is the perfect model for what is happening inside our failed star. As the burner heats the bottom of the pot, the water down there grows hot. Hot water is slightly less dense than cool water, slightly lighter, and so it begins to rise, lifting upward through the cooler water above it. As it rises toward the surface, it gives off its heat, cools down, becomes denser and heavier once more, and sinks back down to the bottom, where it is heated all over again and rises once more. This endless cycle, this rolling overturn of hot material rising and cool material sinking, is convection. It is one of nature's most powerful and most common ways of moving heat, and you have watched it in your own kitchen 1,000 times without naming it. Now scale that humble pot of boiling water up to the size of a giant planet. Fill it not with water, but with crushed metallic hydrogen, and heat it not with a stove burner, but with a searing warmth radiating from its own collapsed core. And you have the interior of a brown dwarf. The entire object, or very nearly all of it, churns and overturns in great convective currents. Down at the bottom, near the hot core, the material is heated and begins to rise. It surges upward through the layers above, carrying the core's heat with it, climbing toward the cooler outer regions of the object. As it rises and reaches those cooler upper layers, it releases its heat, grows denser, and begins the long fall back down toward the core, where the cycle begins again. The whole brown dwarf is one vast, slow, rolling boil, a planet-sized engine of rising and sinking currents, ceaselessly hauling heat from the buried core up toward the surface and the sky. This is the crucial point, the hinge on which our entire story turns. So let me state it plainly. A brown dwarf is convective almost all the way through. Unlike the Earth, which has a solid crust and a more rigid structure that limits how heat moves, the brown dwarf is fluid and churning throughout the great bulk of its body. This means there is a powerful, continuous, planet-spanning system of currents that connects the blazing depths of the interior directly to the cool outer atmosphere where the weather happens. Heat does not merely sit at the bottom, it is actively, vigorously lifted upward, carried by these great rising columns of material from the searing interior all the way up to the visible surface and beyond. And this is precisely why a brown dwarf has weather at all. The convective engine is the thing that lifts the necessary heat, and as we will soon see, the necessary material, high enough into the atmosphere for the spectacular condensation of metals and minerals to take place. Without this churning engine, the brown dwarf would be a dead, static ball, With it, the brown dwarf becomes a stormy, dynamic world. Consider for a moment just how energetic these currents must be. The temperature difference between the core, at millions of degrees, and the upper atmosphere, at perhaps a couple thousand degrees or less, is enormous. Whenever you have a large temperature difference across a fluid body, you get vigorous convection, because the hot material at the bottom is desperate to rise and the cool material at the top is eager to sink. Inside a brown dwarf, that temperature difference is among the largest you will find anywhere in the cosmos outside of a true star, and so the convection is correspondingly fierce. Vast columns of hot material surge upward at speeds that would dwarf any wind on Earth, rising through thousands of kilometers of the interior before reaching the upper layers. Then they spread out, cool, and plunge back down in equally vast descending currents. The whole interior is in constant churning, overturning motion, a perpetual circulation that never rests and never stops. Driven by the simple, relentless flow of heat from hot core to cool surface. This churning has another consequence worth noting, one that ties back to the slow cooling of the brown dwarf over its lifetime. Because the object is so thoroughly mixed by convection, the heat stored deep within it is continuously being brought up to the surface and radiated away into space. The brown dwarf cannot hoard its warmth in the depths forever. The convective currents keep dredging that heat up from below and exposing it to the cold of the void, where it escapes as that faint red and infrared glow we see from afar. This is part of why brown dwarfs cool so steadily and so predictably over time. Their interiors are not sealed vaults of trapped heat, but open, churning systems that efficiently carry their warmth up and out, surrendering it to space across the long ages. The same convection that drives the weather also governs the slow fading of the object. The two processes bound together as parts of a single dying engine. And now we arrive at the threshold of the great revelation, the place where the interior and the atmosphere meet and where everything we have learned comes together. We have descended through the atmosphere and found no surface, only thickening gas. We have watched the temperature climb into the thousands and tens of thousands and beyond. We have felt the pressure mount to millions of times that of Earth, crushing the hydrogen into a strange, degenerate ocean of metallic, electron-shorn liquid. We have discovered that this vast interior is not a furnace of flames, but a churning, convective sea, its currents endlessly hauling heat from the buried core up toward the cool outer skin of the world. We have, in other words, built the engine. We have laid bare the machinery that drives this strange object. But the engine alone is not the show. The show happens where that rising heat meets the cold of space, in the thin and turbulent boundary layer at the top of the atmosphere, where the temperature has finally dropped low enough for something miraculous to occur. Because here is the secret that we have been building toward all along. The convective currents do not merely carry heat upward. They carry material upward too, dredging up the vaporized remains of metals and minerals from the hot depths and lofting them high into the cooler atmosphere. And when scorching hot vaporized rock and vaporized iron, carried aloft by these great rising currents, finally reach the cold upper layers of the sky, they do exactly what water vapor does when it rises into the cold air of Earth. They condense. They gather into clouds. And from those clouds, the most impossible rain in the universe begins to fall. We have built the furnace and the engine. Now, as we rise back toward the surface and turn our eyes to the sky, We are finally ready to witness the moment when solid rock becomes a cloud and metal becomes a storm. We've climbed back up now out of the crushing dark of the interior, and we are hovering once more in the upper atmosphere of our failed star, in that thin and turbulent layer where the rising heat of the convective engine finally meets the cold of space. And I want to begin with a single idea so strange that it deserves to be stated as plainly and as boldly as possible, because everything that follows depends on it. On a brown dwarf, the things we think of as solid become the sky. The rock beneath your feet, the iron that pours molten from a steelworker's furnace, the very minerals that make up the crust of the earth. All of these exist here not as stone and metal, but as vapor, floating in the air, gathering into clouds, and falling as rain. To understand the weather of a brown dwarf, you must first let go of the most basic assumption you carry about matter. The assumption that rock is solid and metal is hard. Here, in these blistering skies, that assumption simply does not hold. Let me build up to why, because the reasoning is beautiful, and it begins with something utterly familiar. Think about water, the most ordinary substance in your life. You know that water can take 3 different forms depending on its temperature. When it is cold enough, below the freezing point, water is a solid. It is ice, hard and rigid, something you can hold in your hand. Warm it up past the freezing point and it becomes a liquid, the flowing water you drink and bathe in. Heat it further, past the boiling point, and it changes again, this time into a gas, an invisible vapor that rises into the air and vanishes from sight. Solid, liquid, gas, ice, water, steam. The same substance, the same molecules, wearing 3 completely different faces depending only on how hot or cold it happens to be. This is one of the first things any child learns about the physical world, and it is the key to everything we are about to witness. Now here is the crucial insight, the one that unlocks the entire mystery of brown dwarf weather. Every substance behaves this way, not just water. Absolutely every material in existence has a temperature at which it melts from solid to liquid, and a higher temperature at which it boils from liquid to gas. We simply do not notice this for most substances, because the temperatures involved are far outside our everyday experience. Take iron, for example. We think of iron as the very definition of hard, solid, permanent stuff. A bar of iron seems about as far from a vapor as anything could be. But heat that iron bar hot enough, and it will melt into a glowing liquid, pouring and flowing like a river of molten orange light. And if you could heat it hotter still, far hotter, the liquid iron would begin to boil, turning into iron vapor, a gas of iron floating in the air. Iron has a melting point and a boiling point exactly the way water does. The only difference is that those temperatures are enormously higher, so high that we almost never reach them in daily life. But the principle is identical. Heat anything enough, and it will become a gas. The same is true of rock. The minerals that make up the stones beneath your feet, the silicates and metal oxides that form the crust of our planet, all of them have melting points and boiling points too. We see molten rock on Earth in the form of lava, glowing liquid stone pouring from volcanoes, rock that has been heated past its melting point deep within the Earth. And if you could heat that rock hotter still, far past the temperature of any lava, it too would eventually boil, turning into rock vapor, a gas of vaporized minerals. On Earth, nothing ever gets that hot at the surface, so we never see it. But the brown dwarf gets that hot, and hotter. In the deep atmosphere of a brown dwarf, where temperatures climb into the thousands of degrees, iron is not a solid, and it is not even a liquid. It is a vapor. Rock is not stone. It is a gas. The materials we consider the most solid things in the world float here as invisible vapors mixed into the hot atmosphere, dredged up from the depths and lofted high by the great convective currents we explored in our descent. This is the starting condition for all brown dwarf weather. Down in the hot lower atmosphere, the air is laced with vaporized metals and vaporized minerals, a hot chemical brew containing iron gas, silicate gas, and a whole array of other vaporized substances, all of them floating freely because the temperature is high enough to keep them in their gaseous form. They behave in this hot lower region much like any gas behaves, mixed into the atmosphere, invisible, carried along by the winds and the rising currents. As long as the temperature stays high enough, these materials remain vapor, and there is no weather to speak of, just a hot, churning, metal-laced gas. But now recall the great engine we discovered inside the brown dwarf, the convection that ceaselessly hauls hot material upward from the depths toward the cooler outer layers of the sky. This is where the magic happens. The convective currents take that hot, metal-rich gas from the deep atmosphere and lift it upward, carrying it higher and higher into the atmosphere. And as the gas rises, something inevitable happens. It cools. Just as the air on Earth grows colder the higher you climb a mountain, the atmosphere of a brown dwarf grows cooler as you rise toward its outer edge, where the warmth radiates away into the cold of space. So the vaporized iron and vaporized rock, lofted upward by the rising currents, find themselves climbing into ever colder layers of the sky. And at a certain height, at a certain critical temperature, the gas becomes too cool to remain a gas any longer. The vapor reaches its condensation point, and it begins to change its form. This is precisely what happens with water vapor on Earth, and the parallel is so perfect that it is worth drawing out in full. Because if you understand a cloud on Earth, you already understand a cloud on a brown dwarf. On Earth, the sun heats the surface, warming the oceans and lakes and damp ground, and that warmth causes water to evaporate, turning liquid water into invisible water vapor that rises into the air. As that vapor rises, it climbs into cooler and cooler layers of the atmosphere, and when it reaches a height where the air is cold enough, the vapor can no longer stay a gas. It condenses, turning back into tiny droplets of liquid water, far too small and light to fall, that hang suspended in the air. Billions upon billions of these tiny droplets clustered together are what we call a cloud. A cloud is nothing more than condensed vapor, a vast collection of microscopic droplets that formed when rising gas cooled past its condensation point. That fluffy white cloud drifting across a summer sky is the visible proof of water vapor that rose, cooled, and condensed. Now take that exact process and replace the water with iron. On a brown dwarf, the convective currents lift hot iron vapor upward into the cooling atmosphere. The vapor rises, the temperature drops, and at a certain height, the iron gas reaches the temperature at which it can no longer remain a gas. And so it condenses, just as water vapor does, turning from iron gas into tiny droplets of liquid iron, microscopic beads of molten metal, so small and light that they hang suspended in the atmosphere. Billions upon billions of these tiny molten iron droplets, clustered together at a particular height in the sky, form a cloud. An iron cloud. A vast deck of suspended liquid metal, glowing dully in the heat, drifting through the atmosphere of the brown dwarf exactly the way a water cloud drifts through the sky of Earth. The physics is identical. Rising vapor, cooling, condensing into suspended droplets. Only the substance has changed from water to molten metal, and iron is only the beginning. The atmosphere of a brown dwarf is rich in many vaporized substances, not just iron, and each of them has its own condensation temperature, its own particular height at which it can no longer remain a gas. Among the most important are the silicates, the family of minerals built around silicon and oxygen that form the bulk of rock on Earth and throughout the cosmos. In the hot lower atmosphere of the brown dwarf, these silicates float as vapor, mixed in with the iron and everything else. But as the rising currents carry them upward into the cooler layers, they too reach a height where they condense. The silicate vapor turns into tiny droplets and grains of liquid and solid mineral, forming clouds of rock. Among these silicate compounds are minerals with names like enstatite and forsterite, magnesium-rich silicates that are among the first rocky materials to condense out of the cooling gas. These are, quite literally, clouds made of the same kinds of minerals that form the stones and mountains of rocky planets, except that here they float in the sky as suspended droplets and grains. Here is something that makes the silicate clouds even more wondrous, and it ties directly to the title of our journey. When silicate material condenses and then is rapidly cooled, it does not always form neat, ordered crystals the way a slowly cooling mineral might. Often it forms an amorphous, glassy solid, silicate glass, the very same family of materials that, when melted and cooled by human hands, becomes the glass in your windows and your drinking cups. The clouds of a brown dwarf are, in a real and literal sense, made partly of glass, of tiny molten and hardening droplets of silicate material drifting through the atmosphere, glittering grains of mineral glass suspended in the hot sky. When astronomers speak of glass falling as rain on these objects, this is what they mean. It is not poetry. It is the direct physical consequence of vaporized rock rising, cooling, and condensing into glassy droplets, exactly as water condenses into rain, but built from silicate minerals instead. There are still more substances at play, condensing at still higher temperatures, in the very deepest and hottest cloud layers. Among the very first materials to condense out of an extremely hot gas, before even the iron and the silicates, are compounds containing aluminum and oxygen, and in particular a remarkably tough mineral called corundum. You may not recognize the name, but you certainly know its more glamorous forms. Corundum, when it contains tiny traces of certain other elements, is what we call ruby and sapphire. The same mineral that forms precious gemstones, beloved and treasured by humanity for thousands of years, condenses in the deep, scorching atmosphere of a brown dwarf, forming clouds of microscopic gem-like particles. Far below the iron clouds and the silicate glass, in the hottest cloud-forming layers, there may drift hazes of corundum, tiny grains of the stuff that rubies and sapphires are made of, condensing out of the cooling vapor like a deck of gemstone dust, suspended in the burning air. There are also compounds of titanium and vanadium, and minerals with names like perovskite, all of them condensing at their own particular temperatures, each forming its own layer in this fantastically complex chemical sky. And this brings us to one of the most elegant and important ideas in the whole of brown dwarf science. The idea that the atmosphere is built in layers, a stack of different cloud decks at different heights, each made of a different substance. The reason for this layering follows directly from everything we have established. Each substance condenses at its own particular temperature. The hottest condensing materials, like the corundum and the other aluminum and titanium compounds, can only condense where it is extremely hot, which means they form their clouds deep down in the atmosphere, in the lowest and hottest cloud-forming layers. The iron, which condenses at a somewhat lower temperature, forms its clouds a little higher up, where the atmosphere has cooled enough for iron vapor to liquefy. The silicates and silicate glass condense at a temperature lower still, forming their clouds higher again. The result is a beautifully ordered structure, a layered sky in which different materials form different cloud decks stacked one above another, sorted by their condensation temperatures, with the most heat-resistant materials forming the deepest clouds, and the more easily condensed materials forming the clouds above them. Picture it as a kind of cosmic layer cake of weather. Deep down, in the hottest cloud-forming region, hazes of corundum and other refractory minerals, the gemstone dust. Above that, a deck of iron clouds, vast sheets of suspended molten metal droplets. Above that, clouds of silicate minerals and silicate glass. And in cooler objects, perhaps still other layers above those, made of materials that can only condense at lower temperatures. Each layer is a cloud deck in its own right, a complete weather system of its own substance, and they are stacked vertically through the atmosphere according to the unbending logic of temperature. As you descend through the atmosphere of a brown dwarf, you would pass down through one cloud deck after another, moving through clouds of glass into clouds of iron into hazes of gemstone dust. Each layer marking a particular temperature at which a particular material makes its transition from vapor to droplet. Now, this layered structure is not the same for every brown dwarf, and understanding why brings us to one of the central tools astronomers use to make sense of these objects. Remember that a brown dwarf cools over its lifetime, fading and chilling across the long ages. A young, hot brown dwarf has a very different atmosphere from an old, cool one, simply because the temperatures are different, and therefore the materials condense at different heights, or in some cases do not condense at all. To organize this enormous variety, astronomers sort brown dwarfs into spectral classes, categories based largely on their temperature and the chemistry of their atmospheres. The most important of these for our story are two classes labelled with the letters L and T, and the difference between them is, in essence, the difference between a sky full of metal and mineral clouds and a sky that has cleared. The hotter brown dwarfs, those classified as L-class objects, are the realm of the iron and silicate clouds we have been describing. These are objects with surface temperatures roughly in the range of well over 1000 degrees, hot enough that iron and silicate materials condense high in the visible atmosphere, forming thick, prominent cloud decks of molten metal and mineral glass. An L-class brown dwarf is a genuinely cloudy world. Its visible atmosphere wrapped in these dramatic layers of condensed metal and rock, and it is in these objects that the spectacular weather of iron rain and glass clouds is most strongly expressed. When you imagine a brown dwarf with skies full of molten iron and silicate glass, you are imagining an L-class object, hot enough for these materials to condense high in the atmosphere, where they dominate the appearance and the weather of the world. As a brown dwarf cools further and ages, it eventually transitions into the cooler T-class, and here something remarkable happens to the clouds. As the object cools, the temperature at which iron and silicates condense moves to deeper and deeper layers of the atmosphere. The cloud decks effectively sink, dropping down out of the visible upper atmosphere into the hidden depths below. In the coolest T-class objects, the iron and silicate clouds have descended so far down that the upper atmosphere has, in a sense, cleared the metal and mineral clouds buried far beneath the visible surface. The chemistry of the upper atmosphere changes too, as new molecules that can only survive at cooler temperatures, such as methane, begin to dominate the spectrum. The transition from L-class to T-class is, in large part, the story of the iron and silicate clouds sinking out of view as the object cools, the dramatic metal weather of the hot L-class objects gradually retreating into the depths as the world fades and chills with age. And the cooling does not stop there. Beyond the T-class lies an even colder category, the realm of the truly frigid failed stars, the Y-class objects, the chilliest brown dwarfs we have ever found. These are the faded ancients, objects so cool that their surface temperatures can drop to the warmth of a summer day, or a cup of tea, or even down toward room temperature, colder than any star has any right to be. By the time a brown dwarf has cooled this far, the iron and silicate clouds that gave the hot L-class worlds their dramatic weather have sunk so deep that they play almost no part in the visible atmosphere at all. The chemistry of the upper sky has been utterly transformed. The change is written in the molecules themselves. In the hot atmospheres of the L-class objects, the searing temperatures tear apart fragile compounds and keep the chemistry simple and metallic. But as the object cools through the T-class and into the Y-class, gentler molecules become possible. Methane, the very same gas that forms in the cold outer atmospheres of the giant planets in our own solar system, begins to appear in abundance, leaving its distinctive fingerprint in the object's light. Water vapor too becomes a major player, surviving in the cooler air where the blistering heat of the hotter objects would once have torn it apart. And in the very coldest Y-class worlds, astronomers suspect that clouds of water itself may finally begin to form. High in the frozen upper atmosphere, the first faint hint of the kind of weather we might almost recognize. Water clouds drifting above the buried, hidden decks of iron and glass far below. There is something poignant in this long progression, this slow, chemical autumn of a failed star. A brown dwarf begins its life, hot and metallic, its skies full of molten iron and silicate glass, the most violent and alien weather in the cosmos. Then, across spans of time longer than the current age of the universe, it cools and fades, its dramatic metal clouds sinking ever deeper, gentler molecules taking their place, until at last, in the cold of extreme old age, it may grow clouds of water not so different from the clouds of a temperate planet, even as it drifts alone and unlit in the dark. The story of a brown dwarf's atmosphere is the story of a world slowly cooling from the unimaginable toward the almost familiar, passing through every strange chemistry in between, a single object that over its enormous lifetime wears the weather of metal, then of mineral, and finally, faintly, of water. It is worth pausing here to be honest and careful about how we know all of this, because the truth matters and the truth is itself fascinating. We have not flown a probe into a brown dwarf. We have never photographed an iron cloud or watched a glass droplet fall. These objects are light years away, far too distant and far too small for us to see their weather directly with any telescope. So how can we speak so confidently about clouds of molten metal and rain of silicate glass? The answer lies in a combination of physics, chemistry, and clever observation. We understand the temperatures and pressures inside these objects from the physics of how they form and cool. We know the condensation temperatures of iron, silicates, corundum, and the other materials from laboratory measurements and chemical theory. Put those two things together, the conditions inside the brown dwarf and the known behavior of these materials, and the formation of these cloud layers follows as a direct and unavoidable consequence. If you have iron vapor in an atmosphere that cools to the right temperature, iron clouds must form. The chemistry demands it, and we have powerful observational support beyond the pure theory. When we capture the light from a brown dwarf and spread it out into a spectrum, breaking it into its component colors the way a prism breaks sunlight into a rainbow, we can read the chemical fingerprints written into that light. Different molecules and materials absorb and emit light at particular characteristic wavelengths, leaving telltale marks in the spectrum. When astronomers examine the spectra of L-class brown dwarfs, they find exactly the signatures they would expect if iron and silicate clouds were present, including features that point to silicate grains in the atmosphere. The light carries the evidence. We see the chemical signatures of these condensed materials, and they match what the physics predicts. So while we have never directly photographed the weather, we have read its fingerprints in the light, and those fingerprints tell a consistent and compelling story of metal and mineral clouds. There is one more crucial point worth making here, and it is a point of honest framing. The specific temperatures and the specific compositions we have discussed are characteristic of particular kinds of brown dwarfs, rather than exact fixed values for every individual object. A given brown dwarf's atmosphere depends on its mass, its age, its temperature, and the precise mix of elements it formed with. One object might have thick iron clouds high in its atmosphere, another, cooler one might have those clouds buried deep below. The picture we are painting is a general portrait drawn from models and from the spectra of many objects, of how these atmospheres are structured and how their clouds form. It is the established physics of cloud condensation applied to the known conditions inside these worlds, supported by observation, but it is a portrait of a class of objects and their characteristic behavior, not a photograph of one particular brown dwarf's exact weather on a particular day. But with all of that honestly said, the conclusion stands, and it is breathtaking. The atmosphere of a hot brown dwarf is a layered, churning, chemically rich sky in which the materials we consider most solid, the iron and the rock and the gemstone minerals, exist as vapor in the hot depths, rise on great convective currents into the cooler heights, and condense into clouds. Clouds of molten iron, clouds of silicate glass, hazes of corundum, the stuff of rubies and sapphires, a vertical stack of weather, each layer a different substance, sorted by the temperature at which it makes its transition from gas to droplet. We have taken the engine we built in the depths, the convection hauling hot material upward, and we have followed that material into the cold of the upper sky, where we have watched it transform. Watch solid rock become a cloud and hard metal become a glittering haze suspended in the burning air. And yet, for all the strangeness of these clouds, we've not yet witnessed the most dramatic act of all. A cloud, after all, is just suspended droplets, hanging quietly in the sky. The droplets are too small and too light to fall, but clouds do not stay quiet forever. On Earth, the droplets in a water cloud sometimes grow large enough and heavy enough to fall, and when they do, we call it rain. The same thing happens here, in these impossible skies. The molten iron droplets and the silicate glass particles do not hang suspended forever. They grow, they gather, and eventually they fall. We have built the clouds. Now we are ready to watch them rain, to witness storms of molten metal and falling glass, to feel the full violence of weather on a world where the sky itself is made of liquefied stone. The clouds are formed. The storm is about to break. We have arrived at last, at the moment everything has been building toward. We have learned what a brown dwarf is. This failed star caught forever between planet and sun. We have descended into its crushed and churning interior and found the great convective engine that drives it. We have followed that engine's raising heat into the cold upper sky and watched vaporized iron and vaporized rock condense into clouds of molten metal and silicate glass. And now, finally, we are ready to watch those clouds do what clouds eventually do. We are ready to watch them rain. So let us hover here in the turbulent upper atmosphere of our hot L-class brown dwarf, surrounded by these impossible clouds, and witness the storm break. Begin with the iron, because iron rain is the image that draws so many people to these objects in the first place, and it deserves to be understood fully. Up in the iron cloud deck, billions upon billions of tiny molten iron droplets hang suspended in the hot atmosphere, each one a microscopic bead of liquid metal, far too small and light to fall on its own. They drift on the winds, jostled by the rising and sinking currents, glowing dully in the surrounding heat. For a while, they simply hang there, the way the droplets in an earthly cloud hang quietly before any rain begins. But these droplets are not static. They are constantly colliding with one another, bumping and merging in the churning air. When two droplets collide, they coalesce, joining into a single larger droplet. And as collision after collision adds more and more liquid iron, the droplets grow, slowly swelling from microscopic beads into larger and heavier drops of molten metal. This is exactly how rain forms on Earth. The tiny droplets in a water cloud collide and merge, growing larger and larger, until at last a droplet becomes too heavy to stay suspended in the air. At that point, gravity wins, and the drop falls. It tumbles out of the cloud and plunges downward, and we feel it as rain. The same process unfolds in the iron clouds of a brown dwarf. The molten iron droplets grow through collision and coalescence until they become too heavy for the atmosphere to hold them aloft. And then they fall, plummeting downward out of the cloud deck as droplets of liquid metal. Rain, iron rain, drops of molten metal, glowing with heat, falling through the burning sky of a failed star. It is one of the most genuinely alien images in all of astronomy. And what makes it so haunting is not that the process is strange, but that it is so ordinary. Swap the iron for water and the meadow for a summer field, and you have described a gentle spring shower. The horror lies entirely in the substance, liquid metal in place of water, falling as rain. Now follow one of these falling iron drops downward, because its journey reveals something profound about the nature of weather on a brown dwarf. Something that makes it even stranger than rain on Earth. On our planet, when rain falls from a cloud, it falls all the way to the ground. It strikes the soil, fills the rivers, returns to the oceans, and there it stays until the sun evaporates it once more. There is a surface for the rain to land on, a definite floor beneath the sky. But a brown dwarf, as we discovered in our descent, has no surface, no solid floor at all. It is gas all the way down, growing hotter and denser with every kilometer. So where does the iron rain go? With no floor to catch it, the drop simply keeps falling into the hotter layers of atmosphere below. And as it descends into that rising heat, something happens to it. It warms. The deeper it falls, the hotter the surrounding gas becomes, until the falling iron drop reaches a depth where the temperature is once again high enough to boil iron. And there, in the hot depths, the molten iron drop evaporates. It turns back into iron vapor. The rain does not land. It vaporizes on the way down and rejoins the gas from which it came. Do you see the cycle that this creates? It is a closed loop, an endless circulation of metal. Iron vapor rises on the convective currents into the cool heights, where it condenses into clouds and falls as molten rain. The rain plunges into the hot depths, where it evaporates back into vapor. And that vapor is then lifted upward once more by the rising currents, back into the cool heights, where it condenses and rains again, around and around, forever, a perpetual cycle of iron rising, condensing, raining, evaporating, and rising again. It is precisely analogous to the water cycle on Earth, the great circulation in which water evaporates from the oceans, rises into the sky, condenses into clouds, falls as rain, flows back to the sea, and evaporates once more. Here on the brown dwarf, it is an iron cycle, a tireless circulation of metal between vapor and liquid, driven by the same convective engine that powers everything else in this world. The iron is never lost and never gained. It simply cycles endlessly between sky and depths, condensing and falling and evaporating and rising, a planet-sized loop of molten metal that has been turning for as long as the object has existed. And the iron is not alone in this. The silicate glass behaves the same way. Up in the silicate cloud deck, the tiny droplets and grains of molten mineral glass grow through collision, just as the iron droplets do, until they become heavy enough to fall. And then they fall, sheets and streamers of silicate glass tumbling downward through the atmosphere, plunging toward the hotter depths below, where they too eventually warm enough to vaporize and rejoin the gas, only to be lifted up and condensed and dropped again in their own endless cycle. So it is not merely iron that rains on a brown dwarf. It is glass as well. Glittering droplets of silicate mineral, the same family of materials that forms window glass, are falling through the sky alongside the iron, each material running its own perpetual circulation, each cycling between the cool cloud-forming heights and the hot vaporizing depths. The skies of a brown dwarf are not just raining metal, they are raining metal and glass at once. A double storm of liquefied stone and molten iron, falling together through the burning air. Pause for a moment and try, as fully as you can, to picture what it would actually be like to be present in such a storm, even though no human ever could survive a single instant there. The air around you is not air at all in any sense you would recognize. It is a dense, scorching gas of hydrogen and helium laced with vaporized metals, hot enough to glow, pressing on you with a force far beyond anything on Earth. Above you and around you hang vast decks of cloud, but these are not the soft white clouds of a summer sky. They are clouds of molten iron and silicate glass, glowing dully in the heat, churning and surging as the convective currents heave material upward and drag it back down. From these clouds falls a rain unlike any rain in the universe you know. Drops of liquid metal and droplets of glass, glowing as they tumble downward, vanishing into the hotter depths below before they ever reach any floor. Because there is no floor, the whole scene glows with its own heat, a sullen red and orange light radiating from the gas itself. A world lit not by any external sun, but by the warmth of its own slowly dying body. It is a vision of weather so extreme, so utterly removed from anything in human experience, that it borders on the unimaginable. And yet, it is real, unfolding right now in the atmospheres of countless failed stars scattered across our galaxy. But the rain, dramatic as it is only one part of the weather. For there to be true weather, there must also be wind, and the winds of a brown dwarf are as ferocious as anything in the cosmos. Think about what drives wind on any world. Wind is simply moving air, and air moves because of differences. Differences in temperature, differences in pressure, differences in heating across the surface of the world. On Earth, the sun heats some regions more than others, the equator more than the poles, the day side more than the night side, and air rushes from one region to another to balance these differences, creating the winds we know. On a brown dwarf, the engine driving the winds is different but even more powerful. It is the colossal heat flowing up from the interior, the fierce convection hauling energy from the depths, combined with the object's rapid rotation. And the result is a system of winds that would shred any earthly storm to nothing. Brown dwarfs, you see, tend to spin extraordinarily fast. Many of them complete a full rotation in just a few hours, whirling around far more quickly than the Earth, which takes a full day to turn once. Imagine a body larger than Jupiter spinning so fast that its day lasts only a handful of hours. This rapid rotation has a dramatic effect on the atmosphere, just as the Earth's rotation organizes our weather into great swirling patterns, into the spiraling storms and the banded winds we see from space. The much faster rotation of a brown dwarf organizes its atmosphere into powerful bands and jets. Vast rivers of wind racing around the object, driven by the rising heat and shaped by the dizzying spin. These winds are thought to reach tremendous speeds, in some cases likely measured in thousands of kilometers per hour, far faster than the fiercest hurricane that has ever torn across the Earth. The atmosphere of a brown dwarf is not a calm and gentle place where rain falls softly. It is a screaming, churning, banded tempest, raked by winds of staggering velocity, with clouds of iron and glass driven before them at speeds that defy comprehension. And within these banded winds, astronomers believe, lurk enormous storms, vast swirling systems, not unlike the great storms we see on the giant planets of our own solar system. You may know of the Great Red Spot on Jupiter, that colossal storm larger than the entire Earth, a cyclone that has raged for centuries in Jupiter's atmosphere. Brown dwarfs are thought to host storms of a similar kind. Immense rotating systems of cloud and wind, regions where the atmosphere churns more violently, where clouds pile up thick or thin, out and clear, swirling features that drift and evolve in the racing bands of wind. These storms can be enormous, spanning vast stretches of the object's surface, dynamic systems of weather that form, persist for a time, and eventually fade, much as storms do on any world, but built from molten metal and glass instead of water and air. Now, here is one of the most remarkable things of all, and it is the key to how we know any of this is true. I told you earlier that we cannot see the weather on a brown dwarf directly, that these objects are far too distant and far too small for any telescope to photograph their clouds. And that is true, but astronomers have found an ingenious way to detect the weather indirectly, to sense the storms without ever seeing them, and the method is beautifully clever. It rests on a simple idea. If a brown dwarf has patchy, uneven clouds, with thick cloudy regions in some places and thinner, clear regions in others, then as the object spins, those different regions will rotate into and out of our view. And because the cloudy regions and the clear regions glow with slightly different brightness, the total amount of light we receive from the object will change as it rotates. A thick cloud deck might trap heat and glow differently from a clear patch where we can see deeper into the warmer interior. Those clearer gaps act like windows, letting our instruments peer down to the hotter layers below, which blaze brightly in the infrared. The high cloud tops, by contrast, sit far cooler and radiate more dimly. So a cloudy face looks faint to us, and a clearer face looks brighter and warmer. So as the brown dwarf turns, presenting first a cloudy face and then a clearer one, its brightness will rise and fall in a regular rhythm, ticking up and down with the period of its rotation. This is precisely what astronomers have observed. They have watched certain brown dwarfs with sensitive telescopes over the course of hours, measuring their brightness with great care, and they have seen exactly this kind of variation, a regular flickering up and down in brightness, repeating with the rotation period of the object. The most natural and widely accepted explanation for this is patchy clouds, uneven weather, regions of thick metal and mineral cloud rotating into and out of view as the object spins. The brightness changes are the fingerprint of the storms, the indirect signature of a patchy, dynamic, ever-changing atmosphere. By watching how the brightness varies, astronomers can even begin to map, in a rough way, where the thicker and thinner cloud regions lie, and how those regions shift and evolve over time. They have effectively detected weather on a world they cannot see, reading the storms in the rise and fall of the object's light. Some of these observations have revealed brown dwarfs whose brightness changes substantially as they rotate, a sign of strikingly patchy, dramatic weather, of clouds that are far from uniform, with thick banks of metal cloud in some regions and clearer skies in others. Over longer stretches of time, astronomers have watched these patterns shift and change, evidence that the weather is not static, but evolving, that storms form and fade, and that the cloud patterns rearrange themselves over days and weeks, just as weather on any world is forever changing. Space telescopes have been particularly powerful tools for this kind of study. Watching brown dwarfs in the infrared light where they shine most brightly, tracking the subtle changes in their glow that betray the churning of their atmospheres. Through these patient observations, the abstract physics of cloud condensation has been confirmed as living, breathing weather, dynamic and variable, raging across these distant failed stars. It is worth dwelling for a moment on just how strange and how singular this weather truly is when you compare it to anything in our own experience, because the contrast is what makes it so extraordinary. Think of the most dramatic weather you have ever witnessed or heard of on Earth. A torrential thunderstorm, with sheets of rain and crashing lightning. A hurricane, with winds tearing roofs from houses. A blizzard burying a city in snow. These are the extremes of weather on our world, and they are built entirely from water and air, from the gentle substances of a temperate planet. The rain is water. The clouds are water. The snow is frozen water. Even the most violent earthly storm is, at its heart, a storm of water moving through air, the same water you drink and the same air you breathe, merely stirred to fury. Now set that beside the weather of a brown dwarf. Here the rain is not water, but molten iron. drops of liquid metal glowing with heat as they fall. The clouds are not water vapor, but vaporized rock and condensed metal. Decks of silicate glass and molten iron, and hazes of the minerals that form rubies and sapphires. The winds are not the gentle breezes of a temperate world, but screaming jets racing at thousands of kilometers per hour, faster than any hurricane, organized by a spin so rapid the whole world turns in mere hours. The temperatures are not the mild range in which water flows, but a searing heat of thousands of degrees, hot enough to keep iron and rock as vapor. There is no gentle ground for the rain to fall upon, no soft meadow or quiet sea, only deeper and hotter gas, into which the metal rain plunges and vaporizes before it can ever land. Every single element of this weather, the rain, the clouds, the wind, the heat, the very absence of any surface, is so far removed from earthly experience that it stretches the meaning of the word weather to its limit. And yet weather it truly is, governed by the same fundamental processes of heating, rising, cooling, condensing and falling that shape the skies of every world, simply pushed to an extreme that nature reserves for the strangest of objects. There is a quiet poetry in this, when you step back and consider the brown dwarf as a whole. Here is an object that reached for the destiny of a star and missed by the smallest of margins, that was born from the same collapsing cloud as the sun's, but never gathered the mass to ignite the steady fire of fusion. It is, in a sense, a failure, a star that never switched on, doomed to fade and cool across the endless ages. And yet, in that very failure, in the peculiar combination of a hot interior and a relatively cool surface that defines a failed star, nature has crafted something that a true star could never possess. A true star is too hot for any of this. In the blazing atmosphere of a real sun, iron and rock could never condense into clouds. Everything is vapor, everything is plasma, far too hot for any droplet to form. It is only in the cooler skies of the failed star, in the strange in-between realm of the brown dwarf, that the temperatures fall into exactly the right range for metals and minerals to make the journey from vapor to cloud to rain. The brown dwarf's failure to become a star is the very thing that gives it this impossible weather. Had it been just a little more massive, had it crossed that threshold and lit its fusion fire, it would have been too hot for clouds of iron and glass to ever form. Its shortcoming is its gift. The star that never was becomes the only kind of object in the cosmos where it can rain molten metal and silicate glass. And these objects are not rare curiosities tucked away in some distant corner of the universe. As our infrared telescopes have grown more powerful, we have come to realize that brown dwarfs are scattered throughout the galaxy in vast numbers, perhaps nearly as common as the stars themselves. The dark spaces between the bright stars are sprinkled with these dim red embers, these cooling failed suns, each one wrapped in its own churning atmosphere of metal and mineral cloud. Some of them drift quite near to us. In our own cosmic neighborhood, dim companions to nearby stars or lonely wanderers in the dark just a few light years away. Right now, as you sit and contemplate these words, countless brown dwarfs across the galaxy are turning slowly in the dark, their banded winds racing, their patchy clouds of iron and glass rotating into and out of starlight, their storms of molten metal raining endlessly into hot depths that have no floor. This weather is not a one-time spectacle. It is a permanent feature of a whole class of objects, unfolding continuously across the galaxy, an enduring storm of liquefied stone repeated in countless skies. our ability to study these worlds is only growing. Each new generation of telescopes peers more deeply into the infrared glow of these objects, reading their spectra with ever greater precision, detecting the chemical fingerprints of their clouds, tracking the subtle changes in their brightness that reveal their churning weather. The most advanced space telescopes now turning their gaze upon brown dwarfs are revealing their atmospheres in unprecedented detail, mapping the chemistry of their clouds and the patterns of their storms, confirming and refining the picture we have built together on this journey. With every observation, the portrait grows richer. We are learning how the cloud layers shift as objects cool, how the weather changes from the hot L-class worlds with their prominent iron and silicate clouds to the cooler T-class worlds where those clouds have sunk into the depths. We are watching from across vast gulfs of space, the weather of failed stars unfold, and each new discovery deepens our wonder at how strange and varied the cosmos truly is. So, let us draw our journey to a close where it began, with the image that first drew us into the dark. Somewhere out there between the stars, a brown dwarf is turning slowly in the void. It glows a deep, sullen red, the fading warmth of a birth that happened long ago, the slow ember light of a body that will spend the rest of eternity cooling toward darkness. It is a star that almost was, a sphere of crushed hydrogen the size of a giant planet, holding within it the mass of dozens of Jupiters, never quite massive enough to light the fire that would have made it a true sun. Beneath its visible skin lies a crushed and churning ocean of metallic hydrogen, held up against gravity by the quantum defiance of its electrons, stirred by great convective currents that haul heat endlessly from its core toward its sky. And in that sky, in the cool upper reaches where the rising heat meets the cold of space, the most impossible weather in the universe plays out. Hour after hour, age after age. Vaporized iron and vaporized rock rise on the currents, cool and condense into vast decks of clouds of molten metal and silicate glass and hazes of gemstone dust. Those clouds, driven by winds of unimaginable speed, swirl into storms that we can detect from light years away in the flickering of the object's light. And from those clouds falls the rain, drops of molten iron and droplets of glass, glowing as they tumble down into the hot depths below, vaporizing before they ever land, rising again to fall once more in an endless cycle that has turned since the object was born. It does not rain water on a brown dwarf, it rains the things we build our world from, the iron and the stone, melted and vaporized, and lifted into the sky to fall again as molten metal and glass. It is weather drawn from the same simple rules that bring rain to a meadow on Earth, the rising and cooling and condensing and falling of vapor, pushed to an extreme so violent and so alien that it transforms the familiar into the unimaginable. And it is happening right now, in countless skies across the galaxy, in the dim red light of countless failed stars, an eternal storm of liquefied stone falling through the dark. The next time you look up at the night sky, remember that hidden between the bright and shining stars are these quieter embers, these almost suns, each one wrapped in clouds of iron and glass, each one raining molten metal into a depthless sky. The universe is far stranger than we ever imagined, and the strangest weather of all falls not on any planet, but inside the failed stars that drift. These dim red embers scattered through the cold, each one hiding its impossible weather from view.